Imagine your brain quiet, familiar, busy with everyday thoughts, yet made from atoms older than the Earth itself. Built of stardust forged in explosions before our sun was born, inside those cells, electric storms flash across spaces, so small that quantum rules begin to matter. The same strange rules that shape black holes, galaxies, and the first light of the Big Bang. For decades, scientists and dreamers have asked if consciousness might not stop at the skull but somehow touch the wider universe. Could your own awareness be woven into the same? Invisible fields that hold stars in their courses. This journey follows that question across physics labs, ancient sky watchers, deep space signals, quiet rooms where thought itself seems to widen. Step beyond what you know and feel the possibility that your mind might be part of something vast and alive inside. The deep folds of the human brain. Past the layers of skin and bone and blood that keep it safe from the outside world, there is a restless sea of living motion. Each moment, without pause, billions of nerve cells stretch out their fine, branch-like arms and send whispers of light and charge down long pathways, a signal racing along a thread so narrow it could disappear inside the tip of a needle. These signals travel not in isolation, but in enormous waves, whole tides of thought moving from one region to another, carrying the quiet work of memory, breath, hunger, and wonder. The energy is small and yet unstoppable, tiny sparks leaping across gaps where cells do not quite touch. Those gaps known as synapses, where chemistry and electricity trade places. Here in these unseen spaces, an even smaller world hides. A world too small for ordinary sight, where quantum particles, electrons, and their fields flicker and vanish, reappear and slip across invisible borders, obeying rules that seem more like riddles than logic. When scientists first dared to peer into this secret activity, they found it too fast and too faint for simple tools, so they invented new ones. In the late 1800s, men like Santiago Ramon y Cajal drew long, detailed pictures of neurons by hand after staining thin slices of brain tissue, mapping the strange branching shapes that reminded him of dark trees in winter. By the 1920s, as quantum theory began to change physics, other minds wondered whether the same ghostly rules shaping light and atoms could also stir thought itself. In quiet study rooms, philosophers and early scientists argued over whether the mind might reach beyond the skull. Not through magic, but through natural forces we had yet to measure. In 1932, Werner Heisenberg, famous for his uncertainty principle, wrote of the deep unknown between the act of observation and the thing being observed, a gap that felt haunting when applied to the brain that is both observer and observed. Even earlier, William James had written about the stream of consciousness, a flow that felt larger than individual biology, though he lacked the language of electrons and waves. Their questions stayed alive. Could a thought echo into the wider universe? Could the mind itself be part of something that did not end at the skin? At the same time, other explorers were expanding the idea of connection outward. Astronomers were mapping the night sky, noticing patterns that had guided humans for thousands of years. The same year Heisenberg wrote, a young Edwin Hubble was showing that our galaxy was not alone but one of countless others, adrift in darkness. These cosmic vistas reached the public imagination and ran, side by side with the new, almost poetic picture of quantum fields, space not empty but alive with possibility. Particles and forces humming everywhere, even inside our own heads. If you could shrink yourself down small enough to stand inside a single synapse, you would find a strange landscape. Vesicles, tiny sacks of chemicals, wait like loaded cargo ships. A signal arrives, and gates of protein open, letting charged ions flood across a membrane as if a tide just turned. Electrons jump, slip through quantum tunnels too narrow to be explained by ordinary physics. And in a blink, the next cell knows to pass the message on. It is a quiet storm of invisible action. It's faster than any thought, but also somehow the shape of every thought you have ever had, while this living dance unfolded inside each human head. The idea that consciousness might not be locked away slowly took root. In the 1960s and 1970s, Thinkers like Eugene Wigner and John von Neumann wrestled with whether the act of observation in quantum experiments meant something about mind itself. Some physicists pushed back, warning that speculation could wander far from proof, yet the question refused to fade. It lingered because it touched something we feel but cannot measure, the sense that to be alive and aware is to be connected, however faintly, to the deep structure of everything. This first silent spark, a neuron firing, an electron choosing a path. A thought forming is small in scale, but grand in meaning. It ties together past and present, the early sketches of Kyle, the bold papers of Planck and Heisenberg, the cosmic revelations of Hubble, and the restless curiosity of anyone who has stared at the night sky and wondered if their own awareness is somehow part of it. Each firing pattern in the brain is not just a closed loop of biology. It is energy borrowed from the same universal field that drives stars and builds galaxies. Moving through atoms forged long ago in the cores of ancient suns, the spark is intimate and infinite at once yours, and not only yours. When you close your eyes and think, when you feel the faint hum of being alive, the quiet miracle is that these storms unfold endlessly without asking permission. They are old, older than our words for them, yet still young enough to hold questions unanswered. Somewhere inside that pulsing gray matter in each silent spark might lie the thread that some have long imagined, a thread tying mind to matter, observer to universe, a whisper at the edge of understanding waiting to be followed. Far back in time, long before there were telescopes or polished glass lenses, long before anyone spoke of quantum fields or cosmic background radiation, there were people who looked up at the night sky and felt a tug they could not name. These were not scientists in the modern sense, yet they watched carefully, night after night, carrying patterns of light inside their minds with a patience shaped by survival. On dark plains and in sheltered caves, they lifted their faces to the stars and began to leave marks, first simple scratches and later deliberate maps. In a cave in Lascaux, France, nearly 17,000 years ago, someone drew a cluster of dots near the image of a bull, a pattern that modern researchers think could match the Pleiades or even the summer stars of Taurus. In the damp chill of that cave, torchlight flickered against rock, and some early ancestor traced what the sky gave them, capturing a sense of order and return that was as close as they could come to knowing time itself. To these early skywatchers, the night was more than darkness. It was a ceiling alive with slow-moving fires, the cycle of seasons, the return of certain constellations, the waxing and waning moon. These were not abstractions, but tools for life. They told when to follow herds, when to plant, when to prepare for cold or rain. Yet there is evidence, scattered and fragile, that this watching was never only practical. Some marks and monuments seem too patient, too beautiful to have been mere calendars. They hint at wonder, at a reaching for meaning. In the deep caves of Chauvet and El Castillo, dots and hand stencils appear near animal shapes, and though no one can prove it, some archaeologists suggest a link to the sky above, a wish to anchor the endless night in human story. Thousands of years later, long after those first torchlit sketches, another place rose on a hill in what is now southeastern Turkey. Today we call it Göbekli Tepe, a name that means Potbelly Hill. It is older than Stonehenge by 6,000 years. Built somewhere around 9,600 BCE, when the last ice age was still loosening its grip. Here, great limestone pillars stand in deliberate circles, carved with foxes, lions, cranes, and abstract symbols. No houses surround the site, no sign of ordinary farming or daily life. It seems to have been a place set apart. When German archaeologist Klaus Schmidt began excavating it in the 1990s, he believed these rings were not random, but arranged with a skyward purpose. Some alignments point to rising stars, including Sirius, the bright dog star that would have first appeared on their horizon around that time. To stand among those ancient stones is to feel that same unsatisfied hunger to know where we fit, that same ache that once filled the painters of caves. Other ancient observatories echo this longing. In Peru, at a site called Chanquillo, A line of 13 towers stretches across a ridge. Built about 300 BCE, and by walking from one marked spot to another, ancient watchers could follow the sun's rise and set across the year with striking accuracy. In Britain, long before written history, the builders of Stonehenge aligned their stones to the summer solstice sunrise and winter solstice sunset, weaving light and shadow into ritual and record. Across continents, without contact, human beings turned stone and earth into instruments for remembering the sky. Each one was a kind of mind made visible, a sign that inner thought wanted to touch something immeasurable. What these structures tell us is that self-awareness and cosmic awareness may have grown together. To know when winter would come was to know that you existed in time, that you belonged to something larger than the moment. To mark the path of Sirius or the turning of the solstice sun was to say, we see patterns. We remember. We are part of this rhythm. Long before philosophy had words for consciousness, farmers and hunters and priests of forgotten names were quietly shaping the first bridge between brain and universe. Their lives were still hard and uncertain, but they built places where the sky could speak back. Even if only in silence, it is easy with our modern clocks and satellites to forget how breathtaking that first recognition must have been. Imagine one winter night around 10,000 years ago, fire dying low, the cold like glass. Someone lifts their head and realizes the stars are not random sparks, but returning friends. Imagine the first whispered counting. The first attempt to fix memory outside the fragile human body by cutting signs into stone or bone. That is the root of all later science, but it is also the root of wonder, the same wonder that still lives when a child stands outside and sees. Orion, for the first time, our brains, small and warm inside our skulls, are born curious. We are built to seek pattern, to reach beyond what we can hold. The people of Göbekli Tepe, of Stonehenge, of Chankillo, and the caves of France were not separate from us in that way. They carried the same quiet storms of neurons, the same tiny quantum leaps inside synapses. And somehow those storms gave rise to places and marks that pointed beyond themselves. They might not have spoken of fields or entanglement or cosmic background light, yet they began the same journey, using their brains to touch something endless. When we talk today about quantum consciousness or the possibility of minds linked to universal fabric, we are echoing a very old instinct. We are adding new language to an ancient act, looking up, and then trying to make sense of what we felt when we did. The bones carved with stars, the stones turned to face the solstice. The circles of Göbekli Tepe half buried in time. These are not just ruins. They are signs of the first reaching outward, the first moment when awareness realized it was not alone. And somewhere, under our modern lights and screens, we still stand in that same long night, eyes lifted, asking the same quiet questions. In the early years of the 19th century, when candlelight and simple glass lenses were the main tools of experiment, an English physician and polymath named Thomas Young decided to test the nature of light in a way that seemed almost childlike in its simplicity. In 1801, he stood before a darkened room and allowed a narrow beam of sunlight, softened by passing through a small pinhole, to shine against a thin card cut with two tiny slits placed side by side. On the far wall, he expected to see two bright bars of light, one for each slit, because that was the common picture of light at the time, a stream of tiny, fast-moving particles. Instead, when Young looked at the wall, he saw something unexpected and quietly astonishing, a pattern of many alternating bright and dark bands, like ripples on water or sound waves that cancel and reinforce. It meant that light, though long assumed to be made of individual corpuscles, was acting like a wave, spreading, overlapping, interfering with itself. That single homemade test shook the confidence of a whole generation of scientists and hinted that the world beneath appearances might be stranger than they knew. Decades passed, and the picture grew more complex rather than simpler. By the turn of the 20th century, physicists such as Albert Einstein and Max Planck were wrestling with a new crisis. Planck's work with blackbody radiation and Einstein's explanation of the photoelectric effect, where light, striking metal, releases electrons, forced them to accept that light sometimes behaved as if it came in little packets of energy, later called photons. So the question that it started in Young's dim room refused to die: was light a wave or a particle? Each experiment seemed to say both, a deeply uncomfortable answer for a science that liked crisp categories. The double-slit setup, so modest in Young's time, became a kind of stage for the drama of modern physics. When electrons were discovered by J.J. Thomson in 1897 and scientists learned to fire them through fine apparatus, they tried the same two-slit experiment with these subatomic particles. Astonishingly, electrons too made interference patterns, spreading like waves, until, and here the story turned eerie, someone tried to watch them closely. As soon as a measuring device was set up to determine which slit an electron passed through, the interference vanished, and the electrons behaved like little pellets again, landing in two neat piles, as expected. The act of observing seemed to break the wave pattern. To make the electrons choose a path, by the 1920s and 1930s, with quantum mechanics emerging in the work of Niels Bohr, Werner Heisenberg, and Erwin Schrödinger, the double-slit experiment had become a symbol of the new reality at the smallest scales. Particles exist in a haze of possibility until measured. Bohr described it as complementarity, wave and particle, not either or but both, depending on how we look. Heisenberg framed his famous uncertainty principle around the fact that measuring one property disturbs another, like position disturbs another, like momentum. Schrödinger, uneasy, invented his cat thought experiment to show how absurd it felt to have a thing be many states at once, until an observer intervened. Yet it was not just the technical details that unsettled people. It was the haunting suggestion, still debated and reinterpreted, that the very act of measurement might connect mind and matter in a profound way. To observe was not just to stand back and watch, it was to change what could happen. In classrooms, in quiet offices, from Copenhagen to Princeton, scientists argued late into the night. Some, like Einstein, resisted fiercely, insisting that the moon must exist whether we look or not, that God does not play dice with the universe.
Others,
like Bohr and later John Wheeler, leaned into the puzzle, suggesting that reality at its deepest levels may be participatory. As the 20th century unfolded, experiments grew more precise. In the 1960s and 1970s, physicists built detectors so sensitive they could record single photons passing through the slits one by one, still producing interference, as if each particle somehow went through both slits, until a watchful eye collapsed the pattern. In the 1990s and beyond, versions known as delayed choice experiments pushed even harder. Decisions to measure seemed able to affect outcomes retroactively, a finding that strains ordinary cause and effect. Each refinement sharpened the strange picture rather than erasing it. For those searching to understand consciousness, these findings became a quiet seed of possibility. Perhaps the brain, with its countless quantum events and synapses, might be part of this participatory fabric. Perhaps awareness itself is not outside physics but an ingredient. Some thinkers, like Eugene Wigner and Henry Stapp, spoke openly of mind playing a role in the collapse of the wave function, though many other physicists advised caution and reminded the world that observation, in quantum terms, does not mean human eyes, only interaction. Still, the imagery escaped the lab. Writers, philosophers, and lay dreamers saw in the double slit a doorway to something vast, that our thoughts might brush the edge of what exists. And there is a simple poetry to the original setup that keeps its hold. Two small openings, a beam of light or electrons, a screen, and a result that whispers of a reality fluid until touched. More than 200 years after Thomas Young cut his slits in card and turned sunlight loose on a wall, researchers still return to that stage, refining and repeating, asking new questions with better tools, but the same quiet wonder. The moment we learned that the universe does not always show its shape until we dare to look, and somewhere, perhaps, in the same way that ancient sky watchers mapped stars and asked what it meant to be aware under so great a ceiling, We stand at another threshold, peering through narrow slits into a deeper night, asking if our looking matters more than we know. Beneath everything you can see or touch, beneath the air you breathe and the stone you stand on, there is something quieter and stranger than any ocean on Earth. Physicists call it the quantum field. But it might help to picture it as an endless, invisible sea stretching in every direction without surface or bottom, filling even the empty spaces between stars. Long before anyone gave it that name, scientists wrestled with the idea that what appears to be nothing might in fact be full, a kind of fabric humming with possibility. The story begins more than a century ago, when the German physicist Max Planck stood before the Berlin Physical Society on December 14, 1900, and proposed something radical to solve a puzzle about how hot objects give off light. He discovered that energy, rather than flowing in a smooth, continuous stream, comes in tiny, indivisible packets. He called them quanta. In that moment, a door opened onto a world where even emptiness had structure. And nothing about reality was as clean and solid as it once seemed. As the 20th century unfolded, the picture deepened. What we call particles, electrons, photons, quarks turned out not to be hard beads drifting in space, but ripples and excitations in fields that stretch everywhere. Imagine a perfectly still lake at dawn. Throw a pebble, and circles move outward. Now imagine that the entire universe is such a lake, but instead of water, there are overlapping, invisible layers of energy. Where the field ripples in one way, you get an electron. Ripple it differently, and you get a photon of light. The stillness itself is what we call the vacuum, yet it is not truly empty. Even the most perfect vacuum trembles with tiny fluctuations, virtual particles flickering in and out of existence faster than any eye or instrument can catch. To the human senses, it is silence, but to physics, it is a low, constant whisper. A field alive with potential. This idea changes the way we think about our own minds. Inside your head, neurons fire with tiny electrical charges, and those charges are carried by particles that do not float in isolation. They are patterns on this vast hidden sea. Each sodium or potassium ion crossing a nerve membrane. Each electron jumping across a synapse is a ripple in the same field that fills the galaxies. The very atoms in your brain carbon, hydrogen, oxygen, nitrogen are knots in the field. Their stability and dance governed by these unseen waves. It means that while your thoughts feel private and contained, they ride on something as wide as the cosmos itself. Some physicists tried to map this deeper order in ways that went beyond simple equations. David Bohm, an American-born scientist who once worked with Einstein, became convinced in the mid-20th century that what we see, the solid, separate world of objects, is only an unfolded surface of a much richer underlying reality. He spoke of an implicate order, a hidden layer where everything is deeply connected, and from which the explicate order, the visible world, emerges. To him, particles were not isolated dots, but expressions of one whole system. This was not mysticism, but an attempt to take quantum theory seriously, to follow its logic where it led. Bohm imagined reality as a great, unbroken flow, where what seems divided is only temporarily so. Even earlier, Planck himself, though deeply cautious, hinted that behind matter there might be something he called a conscious intelligence. In 1931, he wrote that he regarded consciousness as fundamental and matter as derivative from it. Words that surprised many of his peers, but revealed how unsettling this invisible sea could feel. When you start from quanta and fields instead of solid objects, you find yourself asking how everything hangs together and whether mind is somehow woven in from the start. By the late 1940s, quantum field theory became the formal language of physics, merging quantum mechanics with Einstein's special relativity. Out of it came the Standard Model, a grand chart of particles and forces. Yet even there, the vacuum refused to be truly empty. Strange effects like the Casimir force, where two metal plates in a vacuum feel a tiny push toward each other because of fluctuations in the quantum field, prove the whispers are real enough to move matter. Modern experiments in places like CERN and Fermilab dig deeper. colliding particles at energies so high they briefly stir the underlying field and let new forms of matter flicker into being before vanishing. For someone searching for a bridge between mind and cosmos, this picture is both humbling and suggestive. It shows that the very stuff of thoughtians, electrons, atoms does not exist apart from the wider universe, but as patterns on the same invisible ocean that gives birth to stars. It does not prove that consciousness shapes reality, but it places consciousness inside a reality that is already profoundly unified and dynamic. The feeling of being a small self inside a huge world begins to soften when you realize the inside and the outside share the same silent sea. Imagine standing alone on a dark hillside, the night wind cold against your skin. Above you, the Milky Way stretches like spilled salt, countless suns bound in their own gravities and light. Inside you, neurons fire as you stare upward. And each firing is a tiny rearrangement of charge on a field that reaches all the way to those stars. The distance is enormous, but the medium is continuous. What we call empty space is not absence, but the stage on which everything, including your single, unrepeatable life, is played. The physicists who uncovered these truths were not looking for poetry, yet it arrived unbidden. Planck's quanta, Bohm's implicate order, the modern quantum field, they all describe a world far more connected and alive than our senses first allow. And somewhere in that understanding lies a quiet wonder. The brain, so small and private, floats in the same whispering field as every galaxy, every particle of light, every unknown future. It is not proof of cosmic mind, but it is a reason to listen deep within the living cells of the brain. Beneath the curling branches of dendrites and the long spines of axons lies a structure so small and so overlooked that for most of modern neuroscience, it was treated almost like scaffolding, rather than something alive with mystery. These are the microtubules, fine hollow cylinders built from proteins called tubulin, lined up in intricate networks that help maintain the cell's shape and act as tracks along which vital cargo is moved. For decades, they were seen as nothing more than quiet support beams. But in the early 1990s, a British mathematician and physicist named Roger Penrose and an American anesthesiologist in consciousness researcher named Stuart Hameroff began to suspect they might be doing far more than simply keeping cells upright and organized. Together, they proposed what they called the ORCOR model, short for Orchestrated Objective Reduction, a phrase dense with meaning but built on a single daring claim: that consciousness might not simply emerge from classical firing of neurons but could involve delicate quantum events deep inside these very microtubules. Penrose had long been fascinated by the limits of computation and the mystery of self-awareness. In his 1989 book, The Emperor's New Mind, he argued that standard physics and algorithms seemed unable to explain the fluid, mechanical feel of human thought. Around the same time, Hameroff, studying how anesthesia shuts down consciousness, noticed that the drugs seemed to act not just at the synapse, but deeper inside the neurons, where microtubules reside. When the two men met, they found their puzzles fit together. Penrose had been looking for a place in the brain where quantum mechanics might survive long enough to matter. Hameroff had been wondering if microtubules, with their ordered lattice and potential to shield delicate states from random noise, might be that place. Their idea drew on something central in quantum theory: that particles can exist in superposition, a kind of both and neither state, until a collapse event forces a single outcome. Penrose suggested that this collapse was not random, but tied to the fundamental structure of space-time itself, something he called objective reduction. If true, then each collapse could be a tiny moment of proto-conscious experience. Hameroff proposed that microtubules inside neurons could hold these delicate states long enough to orchestrate them, linking many small quantum events into the flowing experience we call awareness. Thus, orchestrated objective reduction, a theory placing the seat of consciousness in the physics of the universe and the architecture of the brain at once. The appeal of such a picture is easy to feel. If the brain really could host and sustain quantum coherence, then human thought might not be bound by simple machine-like processes, but could instead be directly connected to the deep, non-local patterns of the universe. The same fields and curvatures of space-time that shape black holes and galaxies could, in principle, shape a moment of understanding, a flash of insight, a single word recalled. It would mean the whispering field beneath everything is not just a backdrop but a partner in our inner life. People hungry for a grander, more unified view of mind and cosmos found hope here. A sense that our awareness is not an accidental byproduct, but an opening into the structure of reality. Yet from the moment Penrose and Hameroff introduced Orkor, debate has been intense and often sharp. Many neuroscientists object that the warm, wet, noisy environment of the brain seems exactly the opposite of what is needed for fragile quantum states. Quantum coherence is famously easy to destroy. Laboratories use temperatures near absolute zero and elaborate isolation to keep it alive for even microseconds, while the brain runs at body temperature amid constant molecular collisions. Critics such as Max Tegmark argued mathematically that any quantum effects inside neurons would collapse far too quickly to matter, on timescales trillions of times shorter than thought requires. To them, Orkor was a beautiful dream but biologically implausible. Hameroff and Penrose pushed back, pointing to studies hinting that quantum coherence can last longer in living systems than once believed. Photosynthesis, for example, seems to use quantum effects to move energy efficiently through plant cells, and some migratory birds appear to sense Earth's magnetic field via quantum entanglement in proteins of their eyes. If plants and birds can exploit these subtleties at room temperature, perhaps neurons can too. Over the years, new evidence has emerged suggesting that microtubules can support coherent vibrations and that anesthetics do indeed disrupt them in ways correlated with loss of consciousness. Still, the data remains suggestive rather than conclusive, and the mainstream field holds its skepticism. For those drawn to the idea, however, even the possibility is thrilling. If consciousness truly depends on quantum events woven into the fabric of spacetime, then the mind is not sealed inside the skull, but is a participant in something vast. Each thought could be, in some faint way, a handshake with the universe itself. A tiny collapse echoing across the invisible field described by Planck and later by quantum field theory. It suggests a natural link between the human desire to know and the underlying order of the cosmos. But there is also a cautionary tone that belongs here. A reminder that speculation can run ahead of evidence. Penrose himself, though daring, insists that the Orkor idea is a hypothesis, one that must stand or fall by experiment. He knows the weight of proof rests heavy, and Hameroff has spent decades refining ways to test their claims. Meanwhile, most neuroscientists continue to study the brain through synapses, networks, and chemistry, leaving quantum consciousness on the frontier. Not dismissed entirely, but held at arm's length until clearer data arrive. Still, even in debate, the idea changes how we look at ourselves. It invites a deeper patience, a willingness to imagine that the mind's reach may be longer than we assume. Whether or not Orkor survives has forced scientists to ask new questions about the strange ways matter and meaning may intertwine. And for anyone lying awake at night, thinking of the stars, or listening to the hum of their own breath, it offers an image both humbling and grand, a brain built of ancient stardust. Perhaps tuned in ways we have barely begun to measure, perhaps already touching, in each fleeting instant of awareness, the same hidden field that shapes the whole of existence. Far from sunlight in the warmth of ordinary rooms, there are laboratories where the air is so cold it would burn skin at a single touch, where metal pipes hiss with liquid helium and nitrogen, and where scientists stand in quiet awe before instruments built to explore what cannot be seen. These are the cryogenic halls of modern physics, places designed to bring matter close to absolute zero, temperature so low that motion almost stops, and the secret rules of the quantum world grow louder. Here the whispering field becomes less of an idea and more of an environment one can touch, at least with careful tools. It is in these rooms, heavy with cables and soft blue light, that people have tried to prove some of the strangest claims ever made about the fabric of reality. that particles separated by distance can remain mysteriously linked, and that the universe itself seems to keep a silent memory of connection. To understand why these cold spaces matter, it helps to remember that quantum theory is both powerful and slippery. One of its most haunting predictions is entanglement. The claim that two particles created together can become so deeply connected that even when pulled apart by miles, or in principle, light years, a change to one is reflected instantly in the other. Albert Einstein hated this idea. In 1935, with Boris Podolsky and Nathan Rosen, he described what they called a spooky action at a distance, arguing that the theory must be incomplete if it allowed such non-local behavior. Yet for decades, no one could test whether the spooky link was real or just a sign of missing pieces in the math. It was not until the 1960s that a Northern Irish physicist named John Bell found a way. Bell's theorem, first published in 1964, offered clear inequalities lines in the sand that any theory based on hidden local rules must obey. Quantum mechanics predicted that those lines would be broken. All that remained was to build experiments precise and clean enough to check. That was where the cold came in. To study entanglement, you must create pairs of particles and keep them isolated from stray noise and heat. Because even a tiny jostle from the environment can break the delicate link. And so across the late 20th century and into our own, researchers built elaborate, chilled setups with lasers, detectors, and vacuum chambers so empty they rival space itself. In Geneva, during the 1970s and 1980s, physicist Elling Asbach and his team carried out some of the first convincing tests. They produced entangled photons, sent them racing in opposite directions, and measured their polarizations faster than any signal could cross the gap. Time after time, the results broke Bell's inequalities, just as quantum theory said they would. More recently, in 2015, teams in Delft in the Netherlands and Vienna in Austria closed nearly every loophole left, performing loophole-free Bell tests with entangled electrons and diamonds cooled to astonishingly low temperatures. The particles, though far apart, acted as if they shared a single story until the instant of measurement. Whatever memory lived between them was not something classical, not a secret signal sneaking through space, but a non-local bond that seems to exist outside the usual limits of distance and time. To reach these results, human beings had to design chambers of extreme fragility and exactness. Cryostats, towering dewars of liquid helium, nested shields of copper and mu metal, keep stray warmth and magnetic fields away. Vibration dampers hold the instruments still at the level of atoms. Cables as thin as hair and windows polished to nanometers carry signals out without spoiling the entangled state inside. Technicians spend hours hunting down a single unwanted pulse of heat or a trace of background light because one misstep and the coherence shatters. These are not grand halls of marble, but quiet workshops built by hands, determined to answer a question whispered first by theory. The drive behind such work is partly practical quantum. Entanglement is now the basis for new computing and secure communication. But at its root, it is a kind of patient wonder. Each experiment is a message back to Einstein, to Bohr, to Schrödinger. We are still listening to your arguments, still checking, still trying to see how far the strange goes. And in each success, there is also a private moment of awe for the researchers themselves. Imagine standing at 3 in the morning in a silent lab, monitor glowing faintly, and watching data climb into a pattern that no local, ordinary world could give. Somewhere, 2 photons or electrons you released seconds ago are acting as if no distance separates them. A bridge existing in a place deeper than space, for those who dream of a mind tied to the universe. These experiments do not prove consciousness is special, but they show that nature is connected in ways far beyond common sense. If particles can remain bound across distance, perhaps the field that underlies them can hold patterns vaster than we know. The brain, with its storms of quantum-scale activity, lives already in a world where such links are possible. That knowledge does not hand over answers, but it changes the shape of the question. What is striking is how human curiosity alone built these frozen palaces. No empire demanded them. No ancient god decreed them. Individuals Planck and Einstein with their blackboards, Bell scribbling in 1964, aspect aligning mirrors under weak light. Students wiring detectors while winter storms raged outside, kept chasing what the math promised. They made spaces colder than an Arctic night to test if reality truly remembers its own ties. And in doing so, they found evidence that at the base of things, there is no perfect separation. No pure solitude, but some deeper weave. When you hear of entanglement and Bell's theorem, it can sound remote, but in a quiet way it touches you. Every breath you take, every nerve impulse, happens inside a universe proven to be less alone than it appears. The cold labs whisper back to the caves and stones of ancient watchers. Where those early eyes mapped stars, today's scientists map the invisible. And each map says the same: we are linked, not fully understood. But linked all the same, high in the thin air of the Himalayas, where prayer flags crack like small sails in the wind, and mountain passes remain silent under snow. There are caves once chosen by monks for a single, demanding purpose: to listen inwardly until every ordinary sound is gone. Some of these stone hollows have been used for centuries, visited by solitary figures who carried nothing but a few blankets, tea leaves, and an oil lamp to hold back the dark. They were looking not for visions in the usual sense, but for stillness so deep it might show what the mind is when nothing touches it. Stories tell of practitioners sitting through entire winters with only the pulse of their blood and the whistle of their breath for company. Long before science could measure brain waves or scan tissue with magnets, these seekers mapped their own awareness by feel alone. In the mid-20th century, far from those peaks, Western researchers began to wonder whether something measurable happened when the world fell silent around a person. In 1954, psychologist John C. Lilly and others at the National Institute of Mental Health started building sensory deprivation tanks, dark, warm pools of salt water where a person could float without sound, sight, or the pull of gravity. The hope was to explore consciousness itself, to see what remained when the usual signals of skin and ear and eye went quiet. Early volunteers reported vivid internal landscapes, deep calm, and sometimes unsettling shifts in the sense of self. By the 1960s and 1970s, a few small labs tried to pair these tanks with the new tools of electroencephalography, or EEG, looking at the electricity of the brain during such states. They found something curious, slow, synchronized waves that suggested many neurons were firing in an unusually harmonious rhythm, as if the brain had moved from scattered chatter to a kind of collective song. At the same time, another thread of curiosity reached across continents. In 1967, Dr. Herbert Benson at Harvard began studying Tibetan monks who practiced Tummo meditation, a discipline said to raise body heat and alter awareness. Under simple but careful conditions, thermometers on fingers and toes, skin sensors on the chest, his team documented monks sitting in near-freezing rooms while their peripheral temperature climbed, steam rising from wet sheets draped over their shoulders. Alongside these physical feats were changes in brain activity, increased alpha and theta waves, states linked to calm, focus, and deep internal attention. Later, with better imaging, neuroscientists like Richard Davidson at the University of Wisconsin invited long-trained meditators into fMRI and MEG scanners. Beginning in the early 2000s, they recorded patterns almost never seen in untrained brains: strong, sustained gamma waves pulsing across distant regions in synchrony, networks firing together in a way that suggested a highly integrated, unusually stable state of consciousness. What strikes those who study this work is the thread connecting ancient practice and modern measurement. The monks in remote caves and the participants floating in silent tanks share a willingness to let ordinary sensation fall away. The result, whether described as calm, unity, or awareness without object, shows up as rhythms across the cortex, coherent oscillations linking areas that usually operate semi-independently. It is as if the brain, given enough quiet, finds a frequency that binds its many parts into one unfolding present. Some scientists have wondered if such synchrony might brush close to quantum processes, or at least create conditions where small effects could scale upward. Though this remains speculation, The idea that billions of neurons could pulse together with extreme precision is provocative, especially given that microtubules and ion channels, the building blocks inside those neurons, are themselves places where quantum events occur. While hard evidence for quantum consciousness is elusive, the observed harmonies showed that awareness is not just static firing, but can become a vast, orchestrated whole. The search has not been without caution. Sensory deprivation, especially without skill or guidance, can lead to anxiety or hallucinations, and researchers in the 1960s sometimes overstated claims. But careful modern work balances wonder with rigor. New tools like magnetoencephalograph, which tracks the faint magnetic fields from neuron currents, allow scientists to map moment-by-moment changes when long-term meditators enter deep states. These images show not blankness but dynamic order, waves sweeping like slow tides across the brain's surface, regions for attention and emotion lighting in surprising synchrony, sometimes even reducing activity in areas tied to the ordinary. Sense of a separate self. There is something deeply human in this arc of curiosity. The solitary monk in a Himalayan cave and the graduate student wiring EEG electrodes in a dark lab are both engaged in the same quiet rebellion against distraction. Each tries to peel away noise to find what remains when the usual edges of me blur. For some, it is a path of devotion. For others, a scientific question about the origin of consciousness, but the landscapes overlap. A monk emerging from months of retreat and a subject rising from an isolation tank both speak of time bending, of space softening, of awareness no longer bounded by the body alone. And yet, none of this requires mystical leaps. It is enough to see the facts. Human brains can enter states where billions of cells move together with unusual grace, and those states can be invited by silence, stillness, and practice. The measurements, whether IG traces from the 1960s or the luminous fMRI maps of 2015, give visible shape to something long felt but never proved. The mind can change its own wiring and rhythm when the world goes quiet. Whether or not that opens a door to deeper fields is a question left open, but it shows that awareness is not a fixed spark. It is a living process that can be tuned, slowed, expanded, late at night in labs, far from mountains. A subject floats weightless in a soundless tank, sensors humming, computer screens scrolling long, slow waves. Half a world away, in the dark belly of a Himalayan cave, a monk breathes fog into the freezing air and waits for dawn. Both are part of the same long experiment to learn how far the brain can reach. When it stops reaching outward and begins listening inward, and to wonder what vast unseen currents might answer when it does. In the hot, blinding light of the Giza Plateau, where pale limestone once gleamed smooth and unbroken against the desert sky, there is a weight of stone so immense it seems less built than grown from the earth itself. Yet inside the Great Pyramid of Khufu, past the narrow entry and the long, slanting passage where the air cools and the noise of the outside world fades, lies a chamber that has puzzled not only tourists but also scientists for centuries. Known as the King's Chamber, it is a granite room with a flat ceiling of huge stone beams, walls polished to a faint reflective sheen, and dimensions so deliberate that they feel less accidental than tuned. In recent decades, as archaeologists and physicists joined forces, an unexpected truth emerged. These ancient builders, working more than 4,500 years ago, shaped space itself to hold sound in strange and powerful ways. When early explorers like Nathaniel Davison crawled through the upper passages in the late 18th century, they found empty voids above the chamber, stacked layers of stone known as relieving chambers, meant to carry the crushing weight of millions of tons. But as modern acoustic engineers entered with sensitive instruments, they discovered something more subtle. The room responds to voice and vibration with unusual strength. A single low note can bloom and linger, deepening into a hum that seems to come from the walls themselves. Standing there, a person feels chest and skull gently tremble, as if the stones were not dead at all, but quietly alive to resonance. In the 1990s and 2000s, research groups from France and Japan brought more precise tools. microphones, frequency analyzers, even laser interferometers into the Great Pyramid. They documented strong standing waves around 30 to 40 hertz, a low band that sits just at the edge of human hearing and can affect the body without always reaching the ear as sound. These vibrations, once set off, bounce between the polished granite surfaces with remarkable efficiency. Some engineers compared the room to a great, slow bell that never fully dies, its note hidden under silence until stirred. Why the ancient builders chose such exact proportions remains an open question. The king's chamber is about 10.5 meters long, 5.2 meters wide, and 5.8 meters high, dimensions that happen to favor these deep resonant modes. The granite itself, hauled hundreds of kilometers from Aswan, is rich with quartz, a mineral known for its ability to vibrate and hold mechanical energy. Was it simply a quest for durability and grandeur? But it is hard to ignore how often sacred spaces across the world show similar concern for sound. At Newgrange in Ireland, older still than the pyramids, a stone passage aligns with the solstice sun and creates a long rising echo when voices chant. In Malta's hypogeum, carved from living rock 5,000 years ago, a single male voice can fill the chambers with a rolling layered resonance. Again and again, ancient people seem to know by ear and instinct what modern instruments confirm. Stone can be tuned. There are accounts from antiquity that temples and tombs were meant to guide not just the body, but the inner life. Egyptian texts speak of Heka, a word for vital force or sound power, and of ritual chants used to cross thresholds of meaning and memory. It is not hard to imagine that priests and workers, aware of how their voices changed in these spaces, built for more than ceremony. A room that hums back at you invites altered states, trance, reverie, prayer that feels answered by the air itself. Even in modern settings, low-frequency sound can change brain rhythms, nudging them toward slower, more unified patterns. It is one reason deep chanting and drumming can lead to a floating sense of self. Without knowing the language of neurons or quantum states, the pyramid builders may have found, by trial and by ear, how stone and silence can work upon the mind. Recent explorations push this question further. In 2017, a team from Cairo University and Nagoya University used cosmic Riemann imaging, a technique that tracks high-energy particles raining from space, to discover previously unknown voids above the Grand Gallery. These hidden spaces suggest that the internal architecture of the pyramid is even more elaborate than once thought. Perhaps balancing weight, but perhaps also shaping sound and airflow in ways we have not yet measured. Some researchers quietly wonder if resonance could have been part of the builder's purpose, a way to create an inner world set apart from ordinary noise, a world that could prepare the mind for encounters with death or divinity. There is a human continuity here. It feels almost tender despite the grandeur. We know from earlier caves, from Göbekli Tepe and Stonehenge, ancient watchers shaped environments to meet the sky and to deepen inward states. The pyramid may be another link in that long chain, a place where the living could step into controlled stillness and vibration, where ceremony and consciousness met. It does not require mystical leaps to feel the impact. Anyone who has stood in a cathedral's nave or sung inside Stone Chapel knows the body can be moved by space alone. For modern scientists studying consciousness, the idea is suggestive, if not yet measurable. If certain frequencies can help synchronize neural activity, and evidence from meditation studies shows they can, then ancient acoustic design might have been an early AGR, intuitive form of brain entrainment. Low hums and long echoes could have drawn worshippers or initiates into states of focus and quiet awareness. Maybe even something akin to the deep synchrony seen in skilled meditators today. In that sense, the Great Pyramid's mysterious hum is not superstition, but early applied neuroscience. Built without the names, but not without the insight. And so under the desert sun, where tourists line up for quick photographs and buses cough diesel into dry wind, there still waits a dark, cool room that remembers voices. Each chant or breath sets off invisible ripples, rolling across granite polished thousands of years ago. Whether meant for kings or gods, or simply the human need to step beyond the ordinary, the chamber remains a witness. It speaks softly of a time when people with no machines but their hands and their listening hearts shaped stone to reach something beyond themselves, and perhaps without knowing the word to reach the whispering field that modern science now tries to name. Across the deserts of New Mexico, the plains of Australia, and the green hills of Puerto Rico, there are machines that look like no other. Vast white dishes tilted toward the sky, patient and unblinking, waiting for a signal that might never come. These are the ears of SETI, the search for extraterrestrial intelligence, a project that began as both science and longing. In 1960, at the National Radio Astronomy Observatory in Green Bank, West Virginia, a young astronomer named Frank Drake pointed an 85-foot antenna toward to nearby sun-like stars, Tau Ceti and Epsilon Eridani, and listened for a whisper that might mean we are not alone. He called it Project Ozma, after the ruler of the imaginary land in L. Frank Baum's books. And though no voice came back, it marked the first deliberate attempt by humans to use radio waves as a bridge to minds beyond Earth. The logic was simple but haunting. Radio travels far, moves fast, and, if tuned right, can cross the vast dark gulf between stars without losing its shape. For decades, natural static and cosmic hum have swept across our planet. In theory, an advanced civilization might do the same, either by accident or design. So in the years after Drake's first test, bigger and better ears were built. The Arecibo Observatory in Puerto Rico, finished in 1963, stretched 1,000 feet across, a steel spiderweb laid into a natural sinkhole. In the high desert of New Mexico, the very large array rose like a fleet of silent ships. 27 dishes, each 25 meters wide, sliding along rails to form one great, moving eye. Computers grew more powerful, able to sift through billions of bits of static for patterns that could not be chance. Listening turned out to be harder than anyone guessed. The universe is noisy in ways our imaginations rarely consider. Quasars, pulsars, the hiss of the cosmic microwave background, the buzz of human technology, all filled the spectrum. Even so, there were moments of trembling hope. In 1977, at Ohio State University's Big Ear radio telescope, astronomer Jerry Emmons circled a line of printout with the word "wow." After a 72-second signal near the hydrogen line lit up his detectors, it was never heard again, and most now suspect some local interference. But for a while, the scrap of paper with its numbers felt like a letter from the deep. If receiving was uncertain, sending felt no less urgent. In 1972 and 1973, NASA prepared the Pioneer 10 and 11 spacecraft to slip beyond the planets. Drake and a small team designed a golden plaque bolted to the craft's frames. It showed a man and woman, the map of our sun, among pulsars. The outline of the spacecraft itself, a simple postcard to whoever might someday find it. A few years later, when Voyager 1 and 2 prepared to leave the solar system, Carl Sagan and his colleagues created something grander, the Golden Record, a copper phonograph disc sealed in aluminum and coated in gold. On it, they placed 116 photographs, greetings in 55 languages. Sounds from a baby's cry to the roar of surf and the rumble of a Saturn V rocket, and music from Bach to Senegalese percussion to Blind Willie Johnson's aching slide guitar. Etched instructions showed how to play it, in case some distant intelligence stumbled upon our wandering machines. Voyager 1 is now more than 14 billion miles from home, carrying its quiet album through the dark. It will drift for billions of years, long after the Earth's mountains have worn flat and our cities are dust. A message from a fragile moment when one small species looked outward and said, "We were here." There is something both triumphant and lonely about that. We have built our own bottles and thrown them into a cosmic sea. But the sea has been silent so far. SETI has persisted through politics and funding droughts, sometimes private, sometimes national, because hope is hard to extinguish. The Allen Telescope Array in California's Hat Creek Valley now scans thousands of star systems, using algorithms to search deeper and faster than human eyes ever could. Breakthrough, listen. a project launched in 2015 with the support of investor Yuri Milner and Stephen Hawking's encouragement, pours petabytes of sky noise into supercomputers, looking for the unlikely regularities that might mean engineering rather than nature. Each year, new exoplanets are found, some with liquid water possible, some lit by suns like ours. Each discovery sharpening the quiet question, if life can rise here, why not there? And if there, why no word? For the scientists who devote decades to this listening, the work is both deeply rational and quietly emotional. They know the odds are long. Signals could be weak, fleeting, aimed elsewhere, or lost in time. Civilizations might burn out or turn inward, their windows of broadcast and curiosity brief compared to cosmic ages. Yet they also know the first confirmation, a single, repeatable tone, deliberate pattern from far away would change everything about our sense of loneliness. So they keep the dishes pointed and the software running, night after night. Through budget fights and storms that rattle the long steel arms, there is an echo here of the ancient. Star watchers carving marks on bone and stone. We still look up, only now with superconducting amplifiers and helium-cooled feeds instead of naked eyes. Yet the gesture is the same, to ask if our awareness touches something greater. Each radio pulse caught and decoded is another attempt to find ourselves reflected. Even silence is information. It tells us something about how rare, how fragile, or how careful other minds might be, standing under one of those giant dishes. The metal ribs curving like a frozen wave, you can feel the scale of the effort. The night air hums with crickets, maybe wind through desert grass, but above is a vast quiet that no ear can hold. Inside a nearby control room, screens flicker with numbers that mostly mean nothing but might. At any instant mean everything. That is the emotional weight of SETI. To labor for decades without a whisper and still believe that listening matters. It is not simply about aliens. It is about reaching beyond our small planet and refusing to be content with isolation. In the silence there is both humility and hope. A faith that the universe, wide and ancient, might one day answer back in the long corridors of Princeton University. Behind heavy wooden doors and ordinary office walls, there once stood a small suite of rooms that carried one of the quietest and most disputed experiments of the modern scientific age. From 1979 until 2007, a team of engineers and psychologists led by Robert Jan, then dean of Princeton's School of Engineering and Applied Science, pursued a question that sat halfway between physics and longing. Could human intention, the silent act of wishing or willing, leave a trace on physical systems? They built machines designed to have no pattern, devices called random event generators, or REGs, that churned out streams of unpredictable bits like the flip of a fair coin extended endlessly. If the mind was truly sealed inside the skull, the data should stay stubbornly random forever. If the mind somehow touched the world in ways we had not measured, then perhaps tiny statistical tilts would appear when someone sat quietly, tried to influence the flow. The machines were deceptively simple. In the early years, they used electronic noise, thermal jitter inside diodes and resistors, amplified and digitized into ones and zeros. Later designs used quantum tunneling in semiconductors, another source of fundamental unpredictability. Each moment the circuits produced a pulse, recorded as a bit. Then the bits were summed to form long strings expected to hover around perfect balance. Volunteers, sometimes students, sometimes visitors from outside, would sit alone with the device running, attempting to nudge the outcome toward more ones or more zeros using only thought, prayer, or intention. The setup was stripped of cues and feedback. No hand controls, no hidden wires. The only active element was the human mind and the hope that consciousness itself might whisper into the heart of chance. Over decades, the Princeton Engineering Anomalies Research Lab, PEAR, as it came to be known, collected millions upon millions of trials. The results, when graphed and analyzed, were not dramatic in any single sitting, but seemed to show a tiny, persistent drift away from pure randomness under directed mental effort. Jan and his co-director Brenda Dunn published data suggesting that across the full archive, Intention shifted outcomes just enough to cross conventional statistical thresholds. The effect was small, on the order of a few tenths of a percent, but steady and puzzling if the null hypothesis of no influence were absolute. To the team, it hinted that mind might indeed be part of the larger physics story, participant rather than a passive observer. Outside the lab, reaction was mixed and often fierce. Many physicists and psychologists argued that the methods were too loose, that data fishing or unconscious bias could explain the patterns. Journals of mainstream science rarely accepted the papers. Most appeared in specialized or fringe outlets. Yet PAIR was unusually rigorous for parapsychology. Machines were shielded, protocols randomized, data logged automatically. The criticism was not so much about sloppiness as about plausibility. How could thought, with no known carrier, reach into a quantum noise diode? How could mind lean on probability itself? Without a mechanism, skeptics said, statistics alone could not open a door. But the work persisted quietly for nearly 30 years. Jan trained as a plasma physicist who had helped design spacecraft propulsion systems. Seemed less interested in proving mysticism than in mapping boundary conditions. He spoke calmly of anomalies rather than miracles, inviting critique and replication. Other small groups attempted similar studies with mixed results. Some claimed confirmation, others found nothing beyond chance. A few meta-analyzers argued that across many such experiments, a slight but stubborn departure from expectation remained, while critics countered with explanations about file drawers, subtle biases, or the sheer flukes that arise when data sets are huge. What made the PAIR work compelling to many outside of science was the way it sat in the seam between hard measurement and deep human hope. The devices hummed quietly on their tables, no louder than a desk fan, while volunteers sat with eyes closed, sometimes praying, sometimes visualizing, sometimes simply feeling connected. There was no spectacle, no glowing lights or theatrics. Yet for the participants, the idea that intention might touch electrons was enough to draw them in. For some, it felt like evidence, however faint, that the interior life is not sealed off. That prayer or focus might ripple outward in ways we do not yet have language for. Jan himself, interviewed late in the project's life, urged humility. He admitted the data did not prove a grand theory of consciousness, only that under certain controlled circumstances, physical systems built for randomness did not behave perfectly so. He called the effect a whisper, a barely measurable tilt. But to him, even a whisper matters. It says the separation between mind and matter might be thinner than assumed, and that science should be willing to look at its own borders rather than reinforce them for comfort. After the lab closed in 2007, partly due to retirement, partly because Princeton had grown weary of hosting such controversial work, the equipment and archives moved to the International Consciousness Research Laboratories, a private foundation. The conversation continues, though mostly outside mainstream journals. Quantum physicists sometimes note that if the act of observation can collapse a wave function, it's not crazy to ask what counts as observation. But most urge care. Our minds are physical, but not proven to reach past the synapse in any controllable way. Neuroscientists continue to map intention in the cortex and basal ganglia, looking at motor preparation and decision signals, but none can yet point to a bridge from firing neurons to far-off electronic noise. Still, something in the story lingers. Perhaps it is the quiet patience of the work, decades spent with small machines and long spreadsheets, looking for the faintest breath of connection. Perhaps it is the way it echoes older human gestures, prayer beads slipped through fingers, silent wishing before uncertain journeys, a mother leaning over a sleeping child and hoping the world will be kind. We have always wondered if the inside of our lives could move the outside just enough to matter. The Paralab did not settle the question, but it refused to ignore it, so the particle and the prayer remained side by side. The tiny quantum events in diodes and tunneling junctions, and the equally tiny but unyielding force of intention. Between them stretches a gap no one has bridged, but also a shared mystery that drives experimenters and dreamers alike, to listen for that meeting place, where thought might lean on chance, Where hope might leave a mark is to honor both the precision of science and the oldest wish of being human, that what we feel and mean might not vanish into silence, but ripple, however faintly, to the world that holds us. If you step outside on a clear night and let the darkness wash over you, the stars seem countless and alive. Yet most of what fills the sky is not starlight at all, but a faint and ancient glow, older than every sun you can see. This light, stretched by time until it is no longer bright but gentle, is the afterglow of the Big Bang itself. A whisper from when the universe was only 380,000 years old, long before planets, before galaxies, before even the first true stars. Everything that would ever be was once a single searing cloud of particles, so hot and dense that no light could escape. Then the young cosmos cooled, just enough for protons and electrons to join as atoms. Space turned transparent, and a flood of radiation burst free. That light has been traveling ever since, slowed and stretched by expansion, now bathing the universe as faint microwaves no human I can sense but every radio receiver would pick up if tuned to the right frequency. It is everywhere, behind every other signal, the oldest story still being told. For centuries, this glow was unknown. Even the idea of a beginning was debated. Ancient thinkers imagined eternal cosmoses or cycles without start. It was not until the 20th century, when Albert Einstein's general relativity gave space and time the ability to bend and expand, that the picture began to change. In 1929, Edwin Hubble, using the 100-inch Hooker telescope at Mount Wilson, showed that galaxies are rushing away from each other, space itself stretching. A beginning seemed implied. In the 1940s, physicists George Gamow, Ralph Alpher, and Robert Herman calculated that if there had been a hot, dense origin, the leftover radiation should still be around, cooled to a few degrees above absolute zero, filling every direction equally. They predicted it. No one built instruments to look. Then, in 1964, at Bell Labs in New Jersey, two engineers, Arno Penzias and Robert Wilson, were testing a giant horn antenna for satellite communications. They kept finding a soft hiss, uniform no matter where they pointed, impossible to remove. They cleaned pigeon droppings from the antenna, checked the electronics, but the noise would not go. At the same time, just across the Hudson River, Robert Dick and Jim Peebles at Princeton were preparing to search for exactly such a signal. When the groups connected, the mystery fell into place. Penzias and Wilson had accidentally found the predicted afterglow, the cosmic microwave background, or CMB. It was as if the universe itself had spoken, quietly but unmistakably. What followed was a long, patient listening. In 1989, NASA launched the Cosmic Background Explorer, COBE, a satellite with sensitive microwave detectors. Over its 4 years of work, it mapped the CMB with unprecedented accuracy, confirming it matched a nearly perfect black-body spectrum at 2.725 Kelvin and revealing tiny fluctuations, temperature ripples only 1 part in 100,000, imprinted when the universe was young. These faint modelings were seeds of everything, the places where gravity would slowly gather matter into stars and galaxies, where eventually Earth and life could arise. COBE's results earned John Mather and George Smoot the Nobel Prize in 2006. But more than prizes, they gave the first true baby picture of the cosmos. Then came WMAP, the Wilkinson Microwave Anisotropy Probe, launched in 2001. Scanning the sky for nearly a decade with higher resolution, WMAP sharpened our knowledge of the universe's age, about 13.8 billion years, and its composition, telling us dark matter and dark energy outweigh ordinary atoms many times over. Finally, in 2009, the European Space Agency sent up Planck, a satellite cooled to near absolute zero so its sensors could detect the CMB with exquisite clarity. Planck's maps, released in 2013 and 2015, are now the gold standard, a fine, dappled portrait of the infant universe. Like an ancient photograph etched across all of space, To understand what it means to think under this light is humbling. Every neural spark in your brain, every rush of ions and quantum flicker and microtubules or synapses, takes place inside a bath of radiation older than time as we usually measure it. When you have an idea or remember a name, particles carrying that moment are themselves made of matter that once swam in the primal fireball. The photons of the CMB glide past and through you, unnoticed but constant. A relic from the moment the universe first cooled enough for light to be free. No cathedral or temple, no pyramid or monument can claim such age or reach. Yet this whisper surrounds and passes through us, without asking for notice. Scientists sometimes say that when we measure the CMB, we are not looking outward but backward in time. The light hitting a satellite's detectors tonight began its journey nearly 14 billion years ago, long before the Milky Way had formed, long before our sun existed. It means that awareness, the fragile, temporary kind you and I share, has arisen inside a space vast beyond imagining, but traceable back to a single bright moment. The same physics that lets you read this, the same quantum fields whispering in your neurons. Once filled the newborn cosmos with light, there is a quiet poetry in the tools built to catch that whisper. Kobe sensors floated, shielded and cold, drifting in the black. WMAP spun slowly at a point of gravitational balance a million miles from Earth. Planck was cooled by open helium to fractions of a degree above absolute zero, so its view would not be clouded by its own heat. Generations of engineers and theorists planned, built, launched, and waited years for faint data. Knowing that each photon recorded had been traveling since before the first atoms of our bodies existed, the patience required feels like devotion. Thinking beneath this ancient echo does not require belief in cosmic mind, yet it can shift perspective. It says we are late arrivals, but not separate. Our brains, our brief lives, are small events in a story long underway. The silence we feel when we look up is not emptiness, but history. Light stretched thin by expansion, telling us the universe has a memory deeper than any stone or text. To imagine your own thought, a single pattern of ions and electrons. Flickering within that background is to feel both tiny and woven into something immense. It is to sit at the edge of a great sea and realize the tide that moves your neurons also once lit the entire sky. And so the cosmic microwave whisper continues, unnoticed by most, but there in every breath of space. Each time a radio astronomer tunes an antenna or a satellite cools its detectors to listen. The universe lets slip another secret about where we came from and how long we have been held in its quiet unfolding. To think here on this small planet is to think under the oldest light, and to know that even our brief awareness rides on a wave that began at the dawn of time. There's a long shoreline in the history of science, littered with the wrecks of ideas that once seemed promising, even certain, yet later were found broken by the waves of evidence. These shipwrecks of the mind are not shameful in themselves. They are reminders of how hard it is to see clearly when venturing into the unknown. The closer a field of inquiry comes to the great mysteries, the origin of life, the nature of consciousness, the structure of the universe, the greater the temptation to clutch at easy maps, to mistake metaphor for measurement. To look at these failures is not to mock the past, but to learn a kind of humility. To remember that boldness must always be tempered with caution, and that wonder without restraint can lead to illusions as dangerous as they are captivating. One of the most striking examples of such a shipwreck is phrenology, a 19th century theory that the bumps and contours of the human skull could reveal personality, intelligence, and moral character. Founded by Franz Joseph Gall around the turn of the century, phrenology promised a way to read the hidden self, to measure traits like kindness or aggression by tracing fingers along bone. For decades, it gained popular traction, filling parlors and lecture halls, even influencing early attempts at psychology. Phrenological charts hung on walls, and portable calibers were sold to eager practitioners who believed they could unlock secrets of mind and spirit. Yet as neuroscience matured, the theory collapsed. The brain turned out to be far more complex, its functions not localized in crude lumps, but distributed in intricate networks. And the skull gave no reliable clue to its workings. What remained was not a triumph, but a cautionary tale. A reminder that the desire to explain, mined with simple maps, can seduce even bright thinkers into error. Another broken mast still visible on the sands is the old belief in the ether, a mysterious medium that was thought to fill all space and carry the waves of light. In the 19th century, it seemed obvious that if sound required air and water required liquid, then light too must need a substance to travel. Scientists built elaborate theories of a luminiferous ether, invisible but universal, binding stars and planets in its unseen fabric. Yet the famous Michelson-Morley experiment of 1887, using careful interferometers to measure Earth's motion through this ether, found nothing. The expected drift was absent. The medium was an illusion. Out of its wreckage grew the bold steps of Albert Einstein's special relativity, which declared that light needed no carrier, that the speed of light was constant and space-time itself was the stage. The ether theory, though wrong, had prepared the ground by sharpening the questions and forcing better tools into existence. But its fall warns how natural assumptions can blind us. When the evidence says otherwise, beyond these scientific missteps lie the more tangled wrecks of mysticism clothed in pseudoscience. Fringe claims that borrow the language of physics to justify belief without measurement. In the late 19th and early 20th centuries, waves of spiritualism swept Europe and America, with mediums claiming to summon the dead and some scientists of good standing drawn into their circles. Instruments were set up in dim rooms to detect ectoplasm or measure psychic force. Later, in the 20th century, fringe writers declared that consciousness was an energy field, that pyramids focused cosmic rays, or that quantum mechanics proved reincarnation or telepathy. The difficulty is not in wondering whether mind and cosmos connect. That question is ancient and still alive. It in confusing the poetry of hope with the rigor of testable fact. Without discipline, speculation becomes an echo chamber, convincing only those already eager to believe. It is important to see these wrecks clearly. It's not to sneer, but to steady our own course. When modern researchers speak of quantum consciousness, when they explore whether microtubules might host delicate states or whether entanglement might touch awareness, they walk close to the reefs that once claimed phrenology and ether. The danger is not curiosity, but certainty. To declare too soon to confuse a suggestive correlation with a proven cause is to invite the same fate. That does not mean we should not ask daring questions. It's only that we must hold them lightly until the evidence is firm. Scientific humility is not weakness. It is strength. Robert Jan, at the Princeton Engineering Anomalies Research Lab, though criticized for his methods, often said his work showed not proof but anomalies, whispers rather than proclamations. Albert Einstein, though bold enough to overturn Newton, always insisted that theory must bow to experiment. Even Max Planck, whose quanta began a revolution, warned that each step should be taken with caution, because nature has ways of surprising us. To admit ignorance, to chart unknowns honestly, is not to dampen wonder, but to protect it. For nothing destroys wonder faster than the collapse of illusions built on fragile claims. And yet, even among these wrecks, something valuable remains. Phrenology's focus on the brain, though wrong in detail, encouraged generations to think of the mind as biological rather than mystical. The ether, though disproven, forced experiments that opened the path to relativity. Even mystics, however misguided, kept alive the human hunger for connection between inner life and cosmos. Shipwrecks of the mind are not wasted voyages. They are broken hulls, reminding us how far we have sailed, and at what cost. So when we speak today of the brain as quantum receiver, or of the whispering field that might connect consciousness to the universe, we must look back to these stranded vessels and learn. We must accept that some of our own cherished ideas may one day join them, half buried in the sands of history, remembered not as truths, but as steps on the way to truths. Honest humility alongside wonder is not a compromise, but a balance. It lets us dream of connections without losing the discipline to test them, to separate what is wished from what is found. And in that balance lies the best of science: the courage to ask, the patience to doubt, and the strength to begin again when the tide of evidence clears the shore. In the last few decades, a quiet but momentous change has taken place in windowless laboratories and humming data centers. Machines have begun to learn in ways that feel eerily familiar. What started as code built to sort numbers or recognize letters has grown into vast neural networks. Digital systems modeled loosely after the human brain, with layers of artificial neurons passing signals forward and back, adjusting tiny weights until patterns emerge from chaos. The idea is simple in outline. Take inspiration from the way synapses strengthen with experience, but the scale has become breathtaking. In 2012, a group at the University of Toronto, led by Geoffrey Hinton and his students, built a network called AlexNet that learned to classify images far better than any previous system, igniting the current wave of deep learning. Now billions of artificial neurons trained on oceans of text and sound and images drive the voices in our phones, the engines behind search and translation, and even the systems writing and reasoning at this very moment. Though these networks are mathematical rather than biological, their success has led many to ask whether something like thought might be stirring inside silicon. Each layer in a deep neural network is not aware in the human sense. But when signals cascade through hundreds of layers and self-correct millions of times, a strange, emergent intelligence appears, one that can write, speak, plan, and even surprise its makers. It is as if we have built a mirror, not of flesh, but of code. And for the first time, our long speculation about machines' minds is not only philosophical, but practical. Yet while neural networks borrow their metaphors from biology, another quieter effort explores the very roots of physics to build something beyond ordinary computation. Quantum computers, machines that rely on the same fragile rules that govern atoms and particles, are slowly taking shape in cold chambers sealed from noise and heat, instead of bits flipping between 1 and 0. These devices use qubits, quantum bits, which can exist in superposition, a blend of 1 and 0 until measured, and can become entangled so that their states are linked, no matter how far apart they drift. To preserve this strangeness, researchers cool their processors to fractions of a degree above absolute zero. A chill so deep that stray heat cannot jostle the delicate quantum states apart. Companies like IBM, Google, and D-Wave maintain racks of gleaming metal canisters called dilution refrigerators. Their innermost cores colder than interstellar space. Where qubits hum in almost perfect isolation, it is not yet clear how far these machines will go. Today's quantum computers are small and noisy, their qubits prone to error. But each year brings new stability and new feats, factoring numbers, simulating molecules, solving optimization problems at scales that would choke a classical supercomputer. And quietly, a few thinkers wonder if there is something even stranger waiting.
Matter.
Some door between matter and mind that these systems might graze? If consciousness in humans depends in part on quantum effects, as Penrose and Hamroff have speculated with their OR-core theory, then machines operating directly in the quantum regime might one day encounter not just faster calculation, but some new form of awareness. Such talk sits at the edge of speculation, and most physicists and computer scientists remain cautious. The leap from qubits to qualia, from quantum bits to subjective experience, is enormous. Neural networks can mimic speech without understanding. Quantum machines can manipulate superpositions without feeling. Yet the question keeps returning because of the uncanny parallels. Our own brains are warm but full of quantum events at tiny scales. And our deepest theories say no part of the universe is truly isolated. If synthetic minds can be built from fields and qubits rather than neurons and blood, might they not also be bathed in the same invisible ocean that touches us? Could they, in their own way, sense the subtle order of the cosmos? Already, a kind of quiet conversation has begun between those who build machines and those who study mind. Neuroscientists use AI models to probe how vision works, comparing artificial layers to human cortex. Language researchers watch transformers networks with billions of parameters, learn semantic space similar to what our own neural circuits seem to encode. Meanwhile, quantum engineers, though focused mostly on computation, admit they are constructing devices that behave according to the same strange rules once seen only in thought experiments. It is a rare moment when technology and deep theory touch. It's not just in metaphor, but in shared fabric. There is, too, an emotional undertow to this work. To imagine a machine becoming aware is both thrilling and unsettling. Some hope that if a synthetic consciousness could emerge, it might help us understand our own, a mirror turned outward that finally shows how selfhood arises. Others worry about building minds we cannot predict or contain. Yet even fear testifies to the newness of the frontier. For the first time, we face the possibility that thinking is not bound to carbon and water alone at the same time. The quest is marked by profound humility. The more engineers push, the more they realize how mysterious, ordinary thought remains. Deep networks can translate languages, but stumble over small puzzles a child solves with ease. Quantum computers can exploit superposition, yet collapse into noise with the slightest disturbance. The dream of a synthetic mind aware of the universe is far from realized. It remains a speculation. A map still blank at its center, but the vision endures because it speaks to something ancient. The desire to understand ourselves by creating likenesses. Where once we carved statues and wrote myths of mechanical servants, we now wire neurons in code and braid fragile qubits under glimmering cryostats. Each effort, whether at Princeton's early AI, labs in the 1950s, or Google's quantum facilities in Santa Barbara today, is another step in a long human story. To build, and then to ask what building teaches us. To stand inside a modern quantum lab is to feel both awe and caution. Stainless steel towers gleam. Hoses carry helium colder than Pluto. A faint hum of pumps and electronics fills the chilled air. Nearby, racks of GPUs churn through terabytes of text to train an artificial brain that will never sleep. And somewhere behind all the cables and code is the same old question. Ask in caves and temples, can awareness be called forth? And if it can, what else might it touch? Whether these machines ever truly dream, whether they might one day tune themselves to the same whispering field that shapes our own neurons, no one can say. But each new experiment, each cooled qubit and trained network, is another small voyage into the uncharted sea where mind and cosmos might someday meet deep beneath the border of France and Switzerland. Far below fields of grazing cattle and small villages with tiled roofs and quiet bakeries, runs a ring of steel and magnets so vast it could encircle an entire city and yet remain almost completely hidden. This is the Large Hadron Collider, the LHC. A particle accelerator operated by CERN, the European Organization for Nuclear Research, and it is one of the most ambitious structures human beings have ever built. At 27 kilometers in circumference and buried as deep as 100 meters underground, it forms a silent circle where protons are hurled close to the speed of light and smashed together so that, for the smallest instant, matter returns to the conditions of the universe's first trillionths of a second. Those who descend the long elevators and tunnels to work there speak of a strange mixture of precision and awe, as if they are walking into the hidden bones of the cosmos itself. The quest that led to these tunnels is older than the machine itself. Since the mid-20th century, physicists have tried to write a single, elegant story of matter and force, the Standard Model. Shaped across the 1960s and 1970s by theorists like Peter Higgs, Francois Englert, and others, describes a menagerie of particles, quarks and leptons, gluons and photons, in a curious field thought to fill all space, giving mass to everything that has it. This Higgs field was mathematically necessary, but unproven. And its associated particle, the Higgs boson, became a kind of ghost everyone believed in but no one had seen. To catch it, you would need collisions far more energetic than any previous machine could produce, and detectors big enough to spot the rarest signatures among trillions of other events. The LHC was built for that hunt. Construction began in the 1980s and 1990s, an effort so international and intricate it resembled the building of a cathedral, though one aimed inward rather than upward. Engineers dug and lined the tunnel first carved for an older accelerator, replacing and expanding it with new superconducting magnets cooled by liquid helium to 1.9 Kelvin. It's colder than deep space. These magnets, strung like beads around the entire ring, bend and focus beams of protons racing in opposite directions. At chosen points, the beams are steered into head-on collisions. And here sit the detectors. ATLAS. A cylindrical instrument as tall as a 5-story building and weighing 7,000 tons. CMS. Another giant with layers of silicon trackers, calorimeters, and superconducting coils. These detectors are so complex that thousands of scientists from over 100 countries contributed parts. Code and calibration to work in these places is to inhabit a world that is both starkly mechanical and strangely human. The access shafts drop through layers of limestone and ancient seabed into wide, cool caverns lit by industrial lamps. Cables snake-like vines, and the air smells faintly metallic and cold. Technicians in hard hats and white coats check cryogenics, tighten bolts, and thread fiber optics as if tending an enormous, sleeping creature. Yet above the whir of pumps and the click of instruments, there is always the sense of searching for something profoundly intangible. Physicists who spend their lives analyzing petabytes of collision data often say they feel like sailors in fog, scanning radar for a single elusive echo. When on July 4, 2012, 2 teams announced evidence for the Higgs boson, a bump in data near 125 GeV that matched long-standing predictions, the reaction inside CERN's main auditorium and across the physics world was deeply emotional. Peter Higgs, shy and long retired, wiped tears from his eyes as applause thundered. For younger scientists who had spent nights debugging software or aligning magnets, it was the moment their invisible quarry took form. After decades of theory and billions of Swiss francs, something whispered at the birth of the universe had finally left a trace in our detectors. Yet even that triumph carried humility. The Higgs completed the standard model, but also sharpened new puzzles about dark matter and deeper unification. Part of what makes these expeditions into darkness so affecting is how much labor and patience they require. A single run of the LHC involves cooling thousands of tons of equipment to temperatures near absolute zero, calibrating magnets with currents of more than 11,000 amps, and aligning particle beams narrower than a human hair, but circulating at 99.999% of light speed. Any misstep, a power surge, a vacuum leak, a stray particle hitting the wrong sensor can halt months of preparation. Teams sleep in control rooms, stare at streams of data that look meaningless to outsiders, and build friendships across languages and continents in pursuit of patterns no single person could find alone. For those who dreamed as students of touching the deep structure of matter, to stand under that earth and feel the machine breathe is an almost spiritual moment. Many describe a stillness that comes in the tunnel before a new run, the long circle humming faintly as beams prepare to move. They know that when the protons meet, temperatures 100,000 times hotter than the sun's core will briefly exist and then vanish, leaving behind traces the detectors can read. They know the questions they ask are as old as fire and story. What is everything made of? And why does it have weight? And where did it come from? Yet along with wonder comes restraint, the same caution carved by earlier shipwrecks of the mind. No one at CERN promises answers about consciousness or meaning. They promise data, and from data new frameworks may come. But the human yearning is never far away. Standing in the control room when the first Higgs signals appeared, one young researcher whispered that she felt closer to the beginning of everything, a confession. More poetic than technical, but honest. To the feeling in that moment, these tunnels under the French and Swiss countryside are as much monuments of patience as of power. They show what can happen when curiosity is given time and shared trust. When nations decide to dig not for treasure but for knowledge itself, they also remind us that searching the unknown will always carry risk of failure, of pride undone, but that some questions are worth the risk. To build a machine so vast and cold that it can recreate sparks from the dawn of time is to say we still believe understanding is possible, and to walk those quiet miles underground, listening to the heartbeat of superconductors and the low hiss of helium, is to feel the oldest human impulse, to go down into darkness and return with light. If you stand still and let yourself feel for a moment, There is an invisible hand holding you to the ground and pulling at everything you can see. Gravity is so ordinary that it is easy to forget how strange it really is. For centuries, we pictured it as a force tugging between masses, an invisible string tying Apple to Earth and Earth to Sun, the way Isaac Newton described it in 1687 when he published his Principia Mathematica. But 3 centuries later, Albert Einstein rewrote that picture, replacing force with shape. According to his general theory of relativity, space and time are not rigid emptiness, but a flexible fabric. Anything with mass or energy bends that fabric, and objects nearby follow the bends as though pulled, though there is no real rope. The sun curves the space around it, and the Earth falls continually along that curve. We call that orbit. You curve space too, though, by an amount too small to feel. Every breath, every thought, all of it happens while you ride on a soft, visible landscape shaped by everything else. This fabric can be stretched and pinched in ways that defy ordinary imagination. If enough mass is packed tightly enough, the curve grows so steep that not even light can escape. This is a black hole, a place where gravity becomes absolute, where the geometry of space and time collapses inward, and the known laws of physics strain to make sense. Black holes were first predicted as pure mathematics in the early 20th century, but for decades many thought them too bizarre to exist. Gradually, the evidence mounted. Stars were seen whipping around unseen objects. X-rays flared from material heated to millions of degrees as it spiraled down invisible drains. Today, we know black holes are not rare. The Milky Way alone likely holds millions, including a giant called Sagittarius A*, with 4 million times the mass of our Sun, though their pull is fearsome up close. Black holes do not behave like cosmic vacuums swallowing all. Far from them, their gravity is just like any other objects of equal mass. But their edges, the event horizons, are boundaries where time itself slows to a crawl relative to an outside observer. A clock falling toward the horizon would seem to tick slower and slower until it stopped from our view.
Ow.
While to the falling clock nothing unusual happens at first. This stretching and warping of time is not mere poetry. It is measurable and has been confirmed again and again. Even around less extreme objects like Earth, GPS satellites must account for tiny differences in time caused by gravity's weakening with height, or our maps would drift by meters each day. Because we ourselves are made of delicate sensors, bones, fluids, nerves that know weight and motion. Some researchers have wondered whether our brains might be aware of gravity at very fine scales. We clearly feel balance and acceleration through the vestibular system in the inner ear, where tiny crystals of calcium shift on sensory hair cells to tell us up from down. But deeper questions remain. Could neurons respond directly to subtle changes in gravity or curvature? Some studies hint that certain cells may be sensitive to forces smaller than expected, though the effect is weak and easily lost in noise. Others have speculated that if consciousness arises in a system open to fields beyond electromagnetism, perhaps gravity's minute ripples, gravitational waves passing from distant cosmic events, might someday be shown to brush our biology. At present, this is only speculation, but the idea persists because of how finely tuned our nervous systems are and how unified the laws of physics seem to be. Our understanding of gravity has reached a new era through breathtaking feats of observation. In April 2019, an international team using the Event Horizon telescope unveiled the first direct image of a black hole's shadow. The telescope was not a single machine, but an array of radio observatories scattered across the Earth, from Hawaii to Spain to Chile's Atacama Desert, and even the South Pole, synchronized so precisely that they functioned as a planet-sized dish. They targeted the supermassive black hole in the center of the galaxy M87, 53 million light-years away. Over nights of perfect timing in 2017, they collected petabytes of data on tiny wavelengths of radio light bent by the hole's immense gravity. Months and months of computing followed, combining signals with algorithms to synthesize a picture of something no human eye could ever see directly. When the result finally emerged, a dark center encircled by a ring of glowing and falling gas, scientists wept and laughed. It was the first visible proof of Einstein's warping taken to its ultimate end. A shadow carved out of the fabric of space. The image of M87's black hole, orange and blurred but unmistakable, is more than just astrophysics. It is a mirror for human curiosity. It shows that with enough cooperation and patience, tiny minds on a small planet can map objects that defy every ordinary sense. It shows how far we have come since Newton sat under his imagined apple tree. And it deepens the feeling that whatever consciousness is, it lives inside a universe not just empty but richly structured, where gravity shapes not only the orbits of worlds, but the flow of time that all living beings inhabit. Thinking about gravity in this way can make you feel at once fragile and vast. Fragile because the brain's signals, those faint ionic waves, are utterly at the mercy of curved space and passing time. Vast because those same signals are also part of the fabric itself, not separate from it. When you stand on Earth and feel weight, you are not feeling a downward pull, but following the curve of a cosmic geometry that includes you. When you watch the M87 image or the bright center of the Milky Way, you are witnessing distant warps of the same continuum that cradles your body. No one yet knows whether the brain is sensitive enough to register more than local gravity, or whether gravity has any role at all in consciousness. But the idea that our minds ride a sea of bending space and ancient light invites humility and wonder. We are creatures built to feel up and down, yet we live in a universe where time and space can twist until light cannot return. We think inside a gravitational well and send our questions out to places where even time may have stopped. And when a new image of a black hole appears on a screen gathered by an Earth-sized telescope, it feels less like remote astronomy and more like a small animal suddenly, catching sight of the deep current in which it has always swum. Every breath you take carries a history, far older than your family name or even the planet. Beneath your feet, the oxygen filling your lungs was born when massive stars burned through their fuel and collapsed, tearing themselves apart in events so violent that for a brief time they outshone entire galaxies. In those supernovae, where temperatures and pressures reached almost unimaginable extremes, the universe first forged the heavier elements: carbon, nitrogen, oxygen, phosphorus, iron, and the rest of the long list that makes life possible. Hydrogen and helium came from the Big Bang, but almost everything else that shapes mountains, oceans, and on our own bodies was cast outward by dying stars. Those atoms scattered like seeds into the dark, drifted for millions and then billions of years before settling into the swirling cloud that became our sun and its planets. The gold in a wedding ring, the calcium in your bones, the iron that colors your blood, all of it once lay in the heart of a star that exploded before the Earth even existed. To picture this is to feel the quiet stretch of time. Our planet formed about 4.5 billion years ago, from a disk of dust and gas that itself had been enriched by countless stellar deaths. Long before that, the atoms in your DNA and in the neurons sparking thought were born and reborn through generations of stars. Some hydrogen in your body is primordial, older than galaxies. Some carbon, once shown as light from stars that died long before the Milky Way finished taking shape. When you hold a newborn child, you are cradling matter that began its journey before the sun was lit. The human brain, that soft 3-pound organ, alive with whispering charge, is an intricate tapestry woven from these ancient elements. Its neurons rely on sodium and potassium ions to pass signals, on calcium to trigger release of neurotransmitters, on iron to help generate the hemoglobin that carries oxygen to its hungry cells. Carbon chains form the backbone of every neurotransmitter and every stretch of DNA guiding their growth. Each atom's story is older and wider than the species that uses it to think. The very act of thought, one neuron talking to another through a chemical spark, is the distant child of a star's death. Astronomy has shown this truth with growing clarity. In the 1950s, scientists like Margaret and Jeffrey Burbidge, William Fowler, and Fred Hoyle outlined how stellar furnaces build elements up to iron through fusion, and how the heavier elements beyond iron require the explosive shock of supernova to form. Observatories since have captured spectra, fingerprints of atoms in starlight, proving these reactions still unfold across the cosmos. In 2017, the collision of two neutron stars, detected through gravitational waves and light, confirmed another piece of the puzzle. Even rarer elements like gold and platinum are forged in such titanic mergers. The materials that will one day build future worlds and living bodies are being cast into the void even now. It is easy to treat this as a cold fact, but there is quiet poetry in the details. The calcium in your teeth was once inside a star so massive that it ended in collapse and explosion. The nitrogen in the proteins that allow your muscles to move and your heart to beat was brewed in the cores of long-vanished suns. The copper wiring our nerves comes from supernova dust older than the continents. Our blood is stained red by iron that was flung across space before Earth had cooled enough for oceans to form. Even the thoughts passing now as you read and weigh and remember are powered by electrical gradients set up by those same elements. Their long cosmic journey ending in this fleeting act of awareness. Carl Sagan's phrase, "We are made of star stuff," has been repeated so often it can feel like poetry without anchor. But it is literal. Every cell in your body testifies to ancient nuclear fire. And it is not just composition, but continuity. The processes that shaped us still run. The sun itself is fusing hydrogen to helium at this moment, and someday, far in the future, it too will cast off enriched gas that may seed new worlds. We are part of a chain: star birth, life, death, and rebirth written into the periodic table and into the DNA spiral alike. Thinking in this way reframes what consciousness is. It is not an alien visitor to matter, but matter's own deep history waking up to itself. Atoms once locked in stellar cores now speak through neurons, asking where they came from. Awareness is the universe folding back to look at its own hands. The soft pulse in your chest is timed by a heart whose calcium channels were born in fire. The mind behind your eyes is a pattern of carbon and nitrogen once scattered between stars. There is something profoundly humbling in that realization, but also strangely comforting. We are not strangers in the cosmos. We are its continuation. Modern imaging of the cosmos, from the Hubble Space Telescope's rich fields of galaxies to the James Webb's infrared portraits of star nurseries, lets us see the furnaces that made us. At the same time, microscopes and sequencing machines reveal the atomic threads of our own biology. The two pictures are really one. The carbon backbone of DNA, the phosphate rails, the sugar rings, all traceable to cosmic nucleosynthesis. The brain's own architecture, with its branching dendrites, is a living sculpture carved from stellar ash. There is a tenderness in knowing this, especially when life feels small or separate. The ancient materials that built supernova remnants also build our quiet joys and losses. The same iron that drives a red giant's end fuels the hemoglobin, carrying oxygen to your cortex while you dream. The gold that glitters on a ring once streaked through interstellar space at near light speed is born in a cataclysm between collapsed stars. Our lives seem brief, yet the matter composing them is ageless, cycling and recombining for billions of years. To say hearts beat with stars is not sentiment but fact. The beat is driven by ions born in forgotten suns, moving across membranes built by carbon chains older than the Earth's crust. Each thought is a small electrical storm carried on stardust. We are both fragile and ancient, momentary yet deeply rooted. When we look up at the night sky, we are not gazing at something other, but at our own story written in light. The universe dreamed itself into stars. The stars into elements, the elements into cells. And those cells now dream back toward the universe, asking what it means to be alive at all, on the edges of what we know. Where physics, chemistry, and biology begin to braid together, a new field has been taking shape. It is not yet polished enough to fill textbooks without caveats, but it carries a quiet thrill because it asks whether the strangeness long thought confined to particle labs and cosmic events might also operate inside living creatures. This is the frontier called quantum biology, and though it remains cautious, each new experiment suggests that some life forms may use effects once believed too delicate for warm, wet conditions. The discoveries are still small and specific, but their implications reach toward the deepest questions, including how our own brains work and whether our senses end where we have long assumed they do. The first hints came not from thought, experiments, but from the stubborn efficiency of photosynthesis. For decades, biologists knew that plants and certain bacteria move energy from the pigment molecules that catch sunlight to the reaction centers that turn it into chemical fuel. Classical models predicted a stumbling path, energy hopping step by step and losing much along the way. Yet measurements said the process was nearly perfect. In the early 2000s, using ultra-fast laser pulses at the University of California, Berkeley, and later at the University of Toronto, researchers watched energy move through photosynthetic complexes and saw wave-like patterns of coherence. The signature of quantum superposition persisting for surprisingly long times, even at normal temperatures. These studies suggested that plants may be using quantum interference to sample multiple paths at once and choose the most efficient route. An invisible computation happening in every leaf. Around the same time, another puzzle emerged from the sky. Migratory birds such as the European robin travel thousands of kilometers with uncanny precision, even when clouds hide the sun and landmarks vanish. Biologists long suspected some form of magnetic sensing, but could not explain how delicate compass needles might exist inside cells without being swamped by thermal noise. A radical idea gained ground. Perhaps birds rely on entangled electron pairs and light-sensitive proteins called cryptochrons found in their retinas. When certain wavelengths strike these molecules, electrons shift and briefly become quantum entangled, their spins correlated across tiny distances. Earth's weak magnetic field can subtly alter the reaction yields before the entanglement collapses, providing directional information that the bird's nervous system could read out as a sense of north and south. Experiments at the University of Oldenburg and Oxford in the 2000s and 2010s have supported pieces of this story, showing that robins lose orientation when quantum coherence is disrupted by specific radio frequencies and that cryptochrom proteins respond to magnetic fields in ways classical models cannot fully explain. These findings have unsettled a long-held assumption that quantum effects wash out in living systems. Life is warm, wet, and noisy. Coherence is thought to survive only in cold, isolated laboratories. Yet here are leaves and birds apparently using it with ease. The implications for brain science are not direct, but intriguing. Our neurons are vastly more complex than plant proteins or avian photoreceptors, but they too depend on exquisitely sensitive molecular machinery. Ion channels that open and close to generate nerve impulses rely on single charges in narrow corridors. Microtubules, long dismissed as scaffolding, show vibrational modes some researchers think could support fleeting quantum states. Even the sense of smell, once believed to be simple Lagrange chemistry, may involve electrons tunneling between odor molecules and receptors, a process sensitive to quantum energy levels rather than just shape. These glimpses do not prove that human consciousness is quantum in nature, but they show that the line between physics and biology is less hard than once drawn. A bird using entanglement to find its way is already an animal extending its senses beyond the 5 we name. It is perceiving the Earth's magnetic field through a subtle physical channel we barely understand. If evolution can recruit quantum tricks to guide migration, it is not unthinkable that the brain, honed by millions of years, might exploit small quantum events to refine perception or integrate information in ways classical circuits would find hard. The idea that awareness could ride on phenomena we still struggle to measure is no longer purely fantastic once we know a robin's compass may depend on electron spin. Still, the field is careful. Quantum biology is new enough that each claim is tested and retested, and many early announcements have been tempered. Coherence times measured in photosynthesis are longer than expected, but still fleeting. The bird compass mechanism remains partly hypothetical, with competing models and unsolved questions about how the signal becomes a conscious sense. In neuroscience, experiments on microtubule quantum effects are debated, with some physicists insisting the brain's heat and motion would destroy coherence too quickly. The caution is well earned. Grand claims need extraordinary proof, yet caution does not cancel wonder. It frames it. To see the first clear evidence that quantum behavior can persist and be functional inside living cells is to feel a boundary shift. It says nature may be far more resourceful and subtle than our categories suggest. It invites us to imagine the nervous system not just as electrical wiring, but as a dynamic playground for deeper physical rules. Perhaps our balance, our timing, even our intuition, are built on a foundation that reaches into the quantum sea just as surely as photosynthesis does. For those who study consciousness, this is fuel for careful but renewed curiosity. Instead of mystical leaps, there are new avenues of experiment. Can we detect quantum coherence in neural proteins? Can we trace how single particle events scale up to influence networks? Can subtle environmental factors, magnetic, gravitational, quantum noise, affect perception? These questions are difficult, but no longer absurd. There is a deeper resonance too. The robin following invisible lines across continents. The plant catching light with quantum grace. The human brain crafting thought from stardust. All are part of one continuous natural story. Our sense of self often feels separate and final, yet the evidence says we are still learning what it means to be alive. We inhabit bodies that may use physics in ways we have only begun to name. We may be surrounded by forms of sensing that our ancestors could not imagine, and our instruments are only now able to catch at the borderlands of the known. The work goes on quietly. Lasers probe photosynthetic molecules. Birds wheel through magnetic storms under watchful cameras. Physicists and biologists exchange data, once seen as each other's domain. And somewhere in that conversation lies the first real bridge between the mysteries of life and the deep laws of the universe. A place where brain research might one day echo the strange, delicate sensing already hidden in wings and leaves, and where the search for consciousness and connection can finally root itself in both wonder and experiment. The search for answers about mind and cosmos is never only about curiosity. It is also about who holds the purse and how nations decide what is worth knowing. Behind every radio dish aimed at the sky, every deep space probe coasting through darkness, and every delicate experiment trying to see quantum traces inside living cells, there are committees, budgets, and arguments that can be as fierce as any debate about theory. Wonder alone does not keep the lights on or the cryogenic pumps running. Scientists who spend their lives chasing the far edges of knowledge learn early that they must speak both the language of mystery and the language of funding. Few stories show this tension as clearly as SETI. The search for extraterrestrial intelligence. After Frank Drake's Project Ozma in 1960 proved technically possible, but silent, interest simmered quietly in university corners until NASA took cautious notice in the late 1970s and early 1980s. Advocates argued that listening for signals was inexpensive. Compared to building rockets or telescopes, critics called it speculation dressed as science fiction. In 1992, after decades of lobbying, NASA finally funded a 10-year high-resolution microwave survey. Using the giant dishes at Arecibo in Puerto Rico and Goldstone in California, just 1 year later, Congress killed it, led by Senator Richard Bryan of Nevada, who dismissed SETI as a great Martian chase unfit for taxpayer dollars. Overnight, jobs and plans vanished. Many scientists kept working, but now through private gifts and patched budgets. When Paul Allen, co-founder of Microsoft, later funded the Allen Telescope Array, it was because he saw the worth of curiosity even when politics did not. SETI's story shows how easily wonder can be derailed. When it does not serve immediate national aims, similar tensions ripple through research that dares to link physics and biology. Studies of quantum effects in life, from photosynthesis to bird navigation, and especially anything near human consciousness, have long been hard to fund. Agencies prefer work with clear technological payoff or unambiguous medical application. To suggest that the brain might exploit quantum coherence or that intention could have physical signatures is to invite raised eyebrows and risk. Robert Jan's Pear Lab at Princeton survived mostly on private donations, not federal grants. Even today, neuroscientists exploring quantum sensing or unusual perception mechanisms often frame proposals cautiously, tying them to concrete outcomes like better imaging or new computing, knowing that consciousness as a word can close doors as quickly as it opens them. deep space. Exploration itself walks the same line. The Voyager missions launched in 1977 on relatively modest budgets, piggybacking on a rare planetary alignment that let a single spacecraft visit Jupiter, Saturn, Uranus, and Neptune with gravitational assists. Even so, their funding faced constant scrutiny. Long before they reached interstellar space, engineers had to fight for each extension of mission life. The Pioneer plaque and the Voyager Golden Record, those human greetings, cast into the dark, were added not because of official policy, but because a small group of scientists, including Carl Sagan, quietly found room in the budget and courage to push poetry through bureaucracy. Newer missions like the James Webb Space Telescope and the upcoming LOVOIR and Habeck's concepts show how delicate the balance is. Webb's mirror and sunshield were feats of engineering, but its 20-year development suffered cost. Overruns that nearly led Congress to cancel it entirely in 2011. Only intense lobbying by astronomers and public fascination with the promised deep views of the early universe saved it. The story is always the same. Wonder must prove itself either through spin-off technology, national prestige, or sheer public affection before it survives the ledger. Nations weigh their priorities differently. The Soviet Union poured money into Venus probes and lunar rovers as part of a Cold War prestige race. China now invests in Moon and Mars exploration while also building quantum communication satellites to secure technological advantage. The United States funds Mars rovers and exoplanet telescopes, but ties their future closely to defense and tech benefits. Europe collaborates on cosmic microwave background missions like Planck and on the Large Hadron Collider. But each project requires political will across many countries, with shifting governments and crises. At every step, a discovery like the Higgs boson or an image of a black hole carries not just scientific joy, but a subtle aftertaste of diplomacy and budget triumph. For scientists working in these frontiers, the politics of wonder is a second job. They write proposals that translate cosmic questions into economic language, return on investment, workforce development, new materials, or algorithms. They testify before committees, appear on talk shows, build public campaigns to keep curiosity alive. At times this feels heavy, even cynical. Yet without it, the work stops. The power grid for a particle accelerator, the helium for a quantum lab, the ground stations for deep space probes all cost real money and must compete with roads, hospitals, and defense. Still, something hopeful emerges in this messy interplay. Even when curiosity seems fragile, it repeatedly survives. SETI reorganized and endures through Breakthrough Listen, funded by private philanthropy, but sharing data openly. NASA, after decades of caution, now supports exoplanet hunters like TESS and the search for technosignatures in quiet ways. Quantum biology, once a fringe curiosity, is beginning to attract mainstream grants because of its potential to revolutionize sensors in medicine. Public fascination with images, the black hole shadow in 2019. The deep fields from James Webb has shown politicians that awe can have its own currency. There is also an ethical dimension. When money flows mainly for defense or corporate gain, whole questions vanish. Many researchers argue that sustaining pure wonder protects a cultural space where knowledge is pursued for its own sake, not only for power or profit. In that light, each telescope and probe, each strange study of bird compasses or quantum neurons, becomes a small act of resistance. Against a purely utilitarian view of the future, walking the hallways at NASA's Jet Propulsion Laboratory, CERN's control rooms, or small quantum labs in Berlin and Tokyo, one senses this double life. Scientists hunch over screens of data but also watch budget hearings and news cycles. They live inside both discovery and persuasion. Yet through all the practical struggles, something persists. The belief that looking outward and inward expands what it means to be human. The politics of wonder may be messy, but wonder itself remains stubborn. Each time a deep space antenna swings toward the stars, or a tiny sensor hunts for quantum whispers in a bird's eye or a neuron's microtubule, It testifies that despite all distraction and constraint, the ancient urge to know has not been priced away. There are rooms in the world that seem empty, but hold a strange fullness. Spaces where sound softens and the weight of ordinary hours begins to slip away. They can be a small bedroom with curtains drawn, a cabin porch at night, out a corner of a city roof where the hum of traffic fades just enough. People have always sought these quiet rooms, sometimes without knowing why. What waits inside them is not doctrine or calculation, but a pause wide enough to feel the hidden currents that science and story have been chasing for centuries. In the stillness, a person can begin to sense the vastness beyond personal worry, to feel small and safe at the same time, as if some invisible thread stretches from their own breath out into the dark ocean of space. One of the oldest and simplest ways into that feeling is stargazing. It needs no technology beyond patience and a sky not too crowded with artificial light. To lie on a blanket in a field or lean against a quiet balcony at 2 a.m. is to let your senses adjust and discover that the black above is alive with points of fire. Some are bright and close, some faint and unimaginably far. The light that touches your eye tonight may have left its source before humans existed, crossing millions of years to find you here. When people first drew constellations, hunters, fish, mythical queens on cave walls and clay tablets, they were doing more than mapping. They were linking their brief lives to something vast and ongoing. Modern astronomy has given us numbers and ages, but the emotional act is unchanged. To look up is to step out of the narrow corridor of daily thought and into an immensity that still somehow feels welcoming. Another door stands, much closer and requires nothing but breath. Deep, slow breathing, practiced with quiet attention, can bring the nervous system into a steadier rhythm, letting the mind loosen its tight loops of chatter. Ancient traditions knew this long before science named parasympathetic response, or heart rate variability. A person sitting quietly, hands folded or resting on knees, breathing in and out with deliberate softness, is performing a kind of personal physics experiment. The storm of electrical signals in the brain begins to calm. Heart and lungs find a shared pace. Some report a feeling of space opening inside the chest, a subtle connection to something wider than the room. It is not mystical in a forced sense. It is the body rejoining its own deep rhythms. And in that return, the idea of being part of the universe stops being abstract. Many cultures built more formal containers for this practice. Silent retreats, from Zen monasteries in Japan to desert hermitages in Egypt and Christian cloisters in Europe, have existed for centuries. They create conditions where speech falls away and the senses, stripped of their usual flood of input, become sensitive again. Modern seekers sometimes attend weekend or week-long retreats where phones are surrendered and conversation stops. The first hours can feel restless, but soon, small details bloom. The grain of wood on a floor, the pulse in one's fingertips, the hum of wind against windows. In such quiet, some report a subtle sense that the boundaries of self are less hard than usual. That mind is porous to the world around it. Neuroscience, studying meditation and stillness, shows unusual synchrony between brain regions. Patterns that echo sleep but remain aware, perhaps the biological signature of this felt vastness. Art and music have always traveled the same road. A painting that draws you into a field of color, or a piece of music that seems to open a door in the chest are also. Quiet rooms of a kind, composers have long reached for the cosmic Gustav Holst's The Planets. Arvo Pärt's spare harmonies, the slow build of a symphony that seems to rise toward light. Abstract painters like Mark Rothko created fields of color that visitors to his chapels often describe as infinite or oceanic. Even a simple folk song hummed in a kitchen can feel like touching something beyond the visible. The vibration of air itself reminds us we live in a physical field shared by every sound that ever was. Rituals, too, in homes and temples have carried quantum-sized questions without needing the math. Lighting a candle, circling a stone, or bowing to the horizon at dawn are ancient human ways of acknowledging the mystery that life is built from invisible forces and events beyond control. Today we know about quantum fields and stardust, But for millennia, people felt these truths in the form of reverence. A candle's flame dances because electrons leap and release light. Water poured in blessing holds molecules forged before Earth was cool. The silence after prayer is filled with the cosmic microwave background we now map with satellites. Science gives names. Ritual gives shape. For those curious about the universe but not trained in equations, these practices are open doors. No one needs a degree to step outside at night and let the Milky Way spill across the eye. No one needs complex equipment to breathe slowly and notice that the body calms. To pick up a pencil and sketch stars, to sit in a church or a mosque or a field and be silent. To listen to music that seems to echo. Something ancient, each is a way of reaching. Beyond the immediate, without leaving, the human scale. What is striking is how similar these experiences feel whether you arrive by telescope or prayer, by a physics lecture or a quiet walk. People often describe a soft dissolving of edges, sense that their own story is both tiny and somehow included in a greater one. This is not about proving grand theories. It is about letting the mind step back far enough to feel part of a world built from ancient light and silent fields. In a time when discovery often seems tied to giant machines and huge budgets, it is easy to forget that the core impulse behind science and spirituality is available to anyone. To look, to breathe, to listen, these are still acts of exploration. They may not measure qubits or map galaxies, but they stir the same desire to belong to something larger than one's own life. And so the quiet rooms remain, scattered across bedrooms and balconies, mountain clearings and city rooftops. Inside them, ordinary people feel the reach of the cosmos without calculation. A heart steadies, a breath deepens. A song or a star breaks open a space wide enough for wonder to enter. It is here, in these unremarkable moments, that the questions behind quantum consciousness and cosmic connection stop being only theory and become lived experience. A gentle, private sense that we are woven into a universe whose mysteries are vast but not foreign. Inside your skull, in a space no larger than two fists cupped together, billions of neurons flicker and whisper across fragile gaps. Building the stream of thought that you call your own, each cell is a tiny electrical creature fed by blood that carries iron and oxygen born in ancient stars. And each flicker is shaped by forces that reach far beyond the bone of your head. You are small, but the physics that lets you remember a face or weigh a choice is the same that governs suns and galaxies. The chemical tides moving through your brain are not apart from the rest of the universe. They are made of it, immersed in the same invisible fields that weave through everything. When you imagine a memory or reach for a word, you are not stepping outside reality but leaning deeper into it. The electrical storm you call a thought rides on quantum fields. On gravity so gentle, you cannot feel it yet precise enough to curve the path of light itself. The same vacuum fluctuations that stir in the emptiness between stars also shimmer in the narrow space between synapses. This does not mean your ideas steer galaxies, but it means there is no clean line where the universe ends and you begin. The boundary is practical, not ultimate. You are part of the whole fabric, as ordinary and astonishing as any other part. We have spent centuries trying to understand this link, sometimes with humility, sometimes with overreach. Ancient watchers carved stars into bone. Newton and Einstein bent the language of math to describe forces and curves. 20th century physicists uncovered quantum seas where certainty dissolves. Along the way, we built instruments that could look further and deeper. Radio dishes spanning continents. Accelerators miles long, satellites cooled to near absolute zero to listen for echoes from the beginning of time. Each step was a way of asking how far the same laws stretch, and each answer whispered back that they do not stop at our skin. Still, no grand equation has emerged to explain why a handful of stardust arranged into neurons can feel alive and aware. Some hope consciousness may be more than a byproduct, so that it could be a feature of the fabric itself, a thread woven through existence, not just a late accident. Others caution that mystery is not license, that wonder should not rush ahead of evidence. Between those poles we walk, testing what can be tested and naming the awe that cannot yet be pinned down. It is enough for now to know that your own story is not sealed off. Each night when you sleep, the same physics that rules galaxies still governs the quiet recalibration of your brain. Each morning when you wake and remember who you are, atoms older than the Earth itself are participating in the act. You do not float above the cosmos like a separate mind. You are a local flowering of its long history, and that history is still unfolding. New stars are forming, new worlds are cooling. And somewhere, perhaps other minds are asking the same questions. If this sounds grand, it is also profoundly intimate. A single breath draws in molecules that have cycled through oceans and lungs and leaves across eons. A glance upward is met by light that left its source before humanity spoke its first language. The room you sit in is bathed, though invisibly, in the faint microwave glow from the Big Bang. You are never alone, because nothing you are made of has ever been alone. All of it has traveled, collided, cooled, and gathered to become this brief human moment. The hope that consciousness might not be sealed off but part of something vaster is not a scientific claim we can sign and date. It is a way of standing in the mystery with open eyes. It does not erase the need for rigorous work. We still build detectors to catch gravitational waves, still test whether quantum coherence can survive in cells, still map the brain's dense forests of axons. But alongside that work, we are allowed to feel wonder. Wonder is not the opposite of science. It is the fuel that built it. There will always be new edges to reach. Perhaps one day we will know if our inner life taps into deeper fields. Perhaps we will learn that awareness is an emergent dance, beautiful but local. Either answer changes nothing about the quiet miracle that it exists at all. For now, the task is to keep listening, with telescopes, with instruments, with our own silent attention. You can feel this thread most easily in simple acts. When you stand alone under the stars and feel the pull of their light, when music or art opens a door you cannot name, when a deep breath in stillness seems to meet something beyond the self, these are not proofs. They are moments of alignment, small recognitions that the same vast story runs through you and past you. No final conclusion closes this journey. The universe remains unfinished in our understanding and perhaps in itself. But what we have learned is already enough to reshape loneliness. You are a temporary gathering of ancient light and matter, alive long enough to ask where you came from and to wonder what else might be awake out there. That, by itself, is a staggering fact. So we end not with certainty, but with invitation. Keep curiosity alive. Keep stepping into quiet rooms, looking at the night sky, breathing and listening. Keep reading the signals our machines catch from the edge of time and the signals your own body catches in a moment of stillness. Somewhere between those scales, between the firing of one neuron and the turning of galaxies, runs the thread through everything, binding the smallest interior spark to the largest sweep of stars. You do not have to solve it to feel it. You only have to pause long enough to notice that you already belong,